I'm just very pleased Mark had a chance to come and talk to us about this. And as you see, this is work that's done with Google's own and Mark Hill's previous Dr. Michael Marty.
Now we know why we need multi-cores. It's the laptop forever.
That's right. All right, well, I'm very happy to be here, even though I had to get up at 3:30 a.m. Pacific time to be here. Please interrupt me with questions, and I'll try to repeat your question and answer it, because an interactive talk is much more interesting than a one-way lecture. All right, so this started in a bar, actually, when I was talking to IBM's Thomas Puzak, and he says that everyone knows Amdahl's law, but quickly forgets it. And the reason we were having this discussion was the next day I was going to be as part of a debate with Yale Pat, and so this is myself in the middle and Yale Pat and Joel Emmer. I was the only person without a gray beard, so I had my art student daughter correct that. That debate, I was taking the extreme position on parallelism, and this one is a much more balanced position. And what we're going to do is we're going to develop a corollary to Amdahl's law, which says that we're going to have a simple model of multi-core hardware, and it'll complement Amdahl's software model, and for fixed resources, it'll assume fixed resources for the cores, and that core performance will improve sublinearly with resources. Now you'd say, well, this is so simple, how can any consequences possibly follow from that? Well, what we're going to see is that a lot of things follow from that. We, of course, need dramatic increases in parallelism to use increasingly large multi-core chips. But it's worse than you might intuitively think. So if you're 99% perfectly parallel and you have 256 cores, your speed-up's limited to 72. And of course, that's not counting synchronization and communication. So we're going to need a new Moore's law where we're going to try to double parallelism every 2 years. That's what we need. What we get, we'll see. Another interesting consequence of this model is that when we get larger chips with more transistors, we're going to want to increase core performance. This goes against some of the conventional wisdom that we should just deploy a whole bunch of wimpy cores. There's going to be pressure and advantages to doing asymmetric designs where one or a few cores are statically faster, and there are incentives to do dynamic designs where you can shift resources between parallel and serial. And so what I'm going to do in this talk is give you a little background on where research is these days, remind you of Amdahl's law, develop this model, and then apply it to these three kinds of chips. And at the end, I'm going to bring this full circle, and I'm going to try to say, even though this talk is about multi-core chips, that it also has relevance to the warehouse scale computers that Google tries to do. Okay, so just a quick review. We have transistors, we have an integrated circuit. The number of transistors has been doubling rapidly, called Moore's law. We architects have been taking this increasing transistor budget of also faster transistors. We've been doubling core performance every 2 years. While we were incredibly successful, we became invisible to most of computer science. Now that we're failing, you'll know our names again. And so we're moving to these multi-core chips. This is the Sun Niagara that has 8 cores, each of which looks like four cores. So it looks like a 24 or 32-way symmetric multiprocessor on a chip. And we're doing this for power reasons, to tolerate memory latency, such as was pioneered by the great Piranha work that some of you in the audience worked on, to have shorter wires, and to divide and conquer complexity. So the future is going to be more cores, not faster cores. Well, they'll be somewhat faster, but they're not going to double in performance every 2 years. And so the real question is, will chip performance keep doubling somehow? And what we have seen is there's been this virtuous cycle. These are slides due to Jim Laris, where there's been this increased processor performance, which allows for larger, more full-featured software. I would use the term bloated. Larger development teams, higher level languages and abstractions, slower programs, but no problem. Increased processor performance keeps the virtuous cycle going and a lot of money to be made. Okay? What's going to happen now, we're not going to get increased processor performance, at least as defined for the uniprocessor. So what's going to happen? Game over, next level, thread level parallelism and multi-core chips. All right, so how has the architecture research community prepared for this? This is my community. So this shows a histogram of the premier conference in architecture, number of papers that deal with multiprocessors by year, and you can see as we ramped up to multicore, we did this. The lead up to multicore, we went to nothing. And then we're starting to go past that. Unfortunately, I don't have the 2008 data. Luis Barroso is in charge of 2009, so I think that will do very well. But one of the questions I want to ask is, are we going to overreact? Are we going to underreact? Or are we going to react just right? Now, just to pick on some other communities, what about PLDI? So, of course, this begins a lot later. I think PLDI is doing quite well. They're modestly improving or increasing the fraction of papers that deal with multicore, but not overreacting. What about the systems community? This is SOSP in odd years, and then SOSP and OSDI more recently. And you can see that the system community is not paying attention whatsoever. Now, to be fair, little things like the World Wide Web did happen during this interval, which could have caused some distraction. Okay, so on to the meat of the talk. I'm going to remind you first of Amdahl's law. All right, so Amdahl begins with a very simple software assumption, basically a limit argument. A fraction f of an execution time is perfectly parallelizable. There is no problem with scheduling, communication, synchronization. Life is good. On the other hand, 1 minus f is completely serial. There's nothing you can do about it. You just have to wait. And therefore, you can just model the time on one core or one processor in the old days as the serial fraction divided by the rate of one core, 1. And the parallel fraction only running on one core is at the same rate of 1, all normalized to 1. If you have n cores, then what happens is you only speed up the parallel part. And the net result is this speed-up equation, which I'm writing somewhat differently than usual, and you'll see why later. So this was coined in 1967, and Amdahl was trying to stop the move to saying that parallelism was all we needed. He wanted to argue you still needed sequential performance in 1967 because at the time, especially with system software, you were 35% serial, and that tremendously limited you. And his law has applied through the mini computer and PC eras. So what about the multicore era? That's the subject of this talk. All right. So when we design multi-core chips, we have to confront all the degrees of freedom that a single core designer has to confront. Instruction, wake up, select, execution unit, blah, blah, blah. Okay. But you have tremendous number of additional degrees of freedom. How many cores, how big each, shared caches, how many banks, memory interface, on-chip interconnect, et cetera. Okay? And so the purpose of this talk is to not lose the forest for all the trees. We want to have a high-level model to help guide us a little bit. And so remember how simple Amdahl's software model is. So our hardware model is going to be equally simple. Okay? First of all, we're going to say that the chip hardware is roughly partitioned into two things. A bunch of resources that we can use for the cores, and that includes the level 1 cache, and the rest. And I'm going to simplistically assume that the rest doesn't change, and we'll zero in on the resources that apply to cores. That's assumption number 1. Assumption number 2 is that that resource you have for the cores is bounded. You can only spend n resources. I'm not even going to tell you what the unit of n is. Is it area, power, cost, or some other factor? There's a good argument that it's going to be power. Our pictures are going to use area because Marty couldn't draw power. Third assumption is that microarchitects are bright people, and if you give them more resources of this bounded resource, they can make the sequential performance better. Okay? We're going to assume a simple base core normalized to 1 unit of resource, a base core equivalent, with performance 1. Okay? And then you have the option of having an enhanced core where you spend more resources, R resources, and you get performance get garnered by the function performance of R.
Now, is this assumption true in the face of things such as the Itanium?
Is this assumption true in the face of things such as Titanic? Well, these models are at the sort of hand wave level where you don't deal with specific instruction set architectures or even languages. However, once you deal with those things, you can do much worse than what these models project. So these models are upper bounds, if you will. Efficiency frontiers, no guarantee you get anywhere close. By the way, if you're really interested in something interesting, there's a Wikipedia article on Itanium shows sales projections of Itanium as a function of year. You know, it is that funny. All right, so what about this performance R? What does it look like? Well, it turns out if performance R grows faster than linearly with R, you should always enhance the core because it helps both the sequential and the parallel phases. Therefore, our equations are going to assume that the performance grows less fast than linearly. All right, now to do graphs, we have to make some more specific assumptions. And I'm going to assume that the performance grows as the square root of R. So you can have twice the performance for 4 times the resource, 3 times the performance for 9 times the resources. Now, why are we assuming this? Well, initially we started assuming this, quite frankly, because we wanted a function that had no coefficients because we had no data for which to estimate coefficients. But the amazing thing is, talking to people in industry, such as the DEC Alpha people and Intel, they often use the square root law, you know, for initial studies when they don't have the data. So there is some legitimacy, and furthermore, the equations work for any function. Okay, so how are you going to speed up these enhanced cores? Not the subject of this talk. All right, that's it for the model. Pretty simple, but amazingly, you're going to see that there's a bunch of implications that follow from it. So first of all, symmetric multi-core chips. Okay, so each chip has a bound on its resources. You can spend n resources on the cores. Each core is going to have r resources. Symmetric multi-core means all cores identical. Therefore, you have n divided by r cores per chip using a continuous approximation because n divided by r times r equals n, which is an example of the high-order math in computer architecture. Okay, so pictorially, if you have 16 resources to spend, you can have 16 cores. Of course, you have to have the other stuff not drawn. You could have four BCE cores, and you could have 1 16 BCE core. All right, so how does this affect performance? Okay, the serial fraction 1 minus f uses 1 core at the rate performance r. So the serial time is the fraction divided by the rate. The parallel fraction uses all the cores at this performance r rate, and so you get this equation right here. And therefore, the speed up with respect to one base core is sort of a richer version of Amdahl's law, where this performance r takes effect. And what you see is that the enhanced cores potentially speed up both the serial and the parallel parts. Well, not really, because this parallel part over here has this r in the numerator, which is bad because it's growing faster than this performance r. So there's going to be a trade-off. Now, if you're mathematicians, we're done. You can look at this equation, and all implications can follow from it. For the rest of us, we're going to plot some graphs, and that's going to require the square root assumption. Okay, so here's a graph, and I'm going to explain the axis because there's a bunch, I'm going to have many graphs like this. Okay, so the y-axis is speed up with respect to one base core. At the top of the slide, we see we're using 6 resources for 16 base cores. And then the x-axis has this r BCEs, which is the amount of resources we're going to spend on each core in our symmetric multi-core. So if we spend 1 resource, there's going to be 16 cores, 2 resources per core, 8 cores, etc. Okay, and finally now this first line shows if our fraction parallel is 50% and we have 16 cores to spend, you ought to spend them on 1 core and get the square root of 16 as your speed up. And so if you only have 50% parallel, multi-core is not the optimal thing to do. And I wonder if some client workloads are in this situation. So obviously, we need to increase parallelism to make multi-core optimal. This is not shocking. All right, if your parallelism is 90%, which is not bad, multi-core becomes optimal. It's optimal to spend 2 resources on a core, have 8 cores, and you get a speed up of a disappointing 6.7. And so, you know, you have to have more parallelism for this to really do amazing things. Okay, and so if your parallelism asymptotically approaches 100%, of course, things are totally wonderful. So even though I'm going to talk later about how we want to speed up cores, let's not forget the most important thing for using multicore is to get the fraction parallel up. And so many people should definitely target that. And so, you know, a way of thinking about this is that we have this technologist Moore's law where you double the number of transistors per chip every 2 years. This is still happening. You have the microarchitect's Moore's law where you double the performance per core every 2 years. This ran for a long time but has stopped largely. And we're going to need a third Moore's law for multicore. Architects can double the number of cores per chip, but what about somehow we have to double the parallelism per chip? And maybe we can have some architectural support. And then the net result might be to double the performance per chip every 2 years. And so to me, this is fascinating because for the first time, software has to be a producer, not consumer of performance gains. All right, back to the hardware. So this is our graph with 16 base core equivalents, okay? And Moore's law is still running. And so we're going to be able to build chips that could have 256 base core equivalents. So the question is, should you have more cores? Should you enhance the cores, or both? Who thinks more cores? Enhance the cores. Both. Okay. The answer, of course, like anything in life, is it depends. Okay? So here's our case. This was 90% parallel. We had 8 cores for a speed up of 6.7. If we now go to 256 BCEs, for 90% parallel, you should have 9 cores, which is only 1 more than 8. You get a much bigger speed up. You should spend all your work on enhancing the cores. We're now using 28 resources on each core. Obviously, if you have almost perfect speed up, you should only spend it on more cores. However, there are plenty of regimes like a middling level of parallelism. I hate to call 99% a middling level of parallelism. The optimal thing to do is increase the base cores to 3 resources, and instead of having 16 of them, have 85 of them. Okay? So as Moore's law increases in, we often need to enhance the core designs. So we shouldn't stop figuring out how to do that, like there's a danger of doing right now. So F really matters. I'll just put these up real fast. And, you know, at 99% parallel, that's really not enough to use 256 effectively. And people like Berkeley and Stanford are talking about 1K cores. And there you're even losing half your performance with only 99.9% parallel. Yes?
Given that some types of programs may not really ever have any significant portion where all the threads have to sort of join and go to a single thread, but maybe they have, you know, lock contention so that some subset is joined, how should I interpret a number like 0.99?
Well, I'll give you, so the question was, Amdahl's, I'll rephrase your question. Amdahl's software model is incredibly naive, isn't it, Mark? That it only has a parallel phase and a sequential phase when in fact, you know, you can have maybe no sequential bottlenecks, but you can have imbalances due to locking that doesn't affect everyone. I'll address that a little bit at the end, but I think on balance, I'm not addressing that. I'll tell you, by the way, a way that Google can estimate F for its workloads, but we will need richer models, right? And this is just a very simple one. Okay, I just want to add one thing, though, that there's this naive belief that if your speed up on C cores is less than C, that this is a bad idea, that you should never deploy such a system. Okay, and David Wood and I wrote this article a dozen years ago, and we defined something called cost up, which is how much more does the C cores or C processors cost you relative to a uniprocessor? And even back then, on the SGI Power Challenge, which was developed in one of these buildings right here, a 32 processor system, the cost up was 8.6, meaning the 32 processor system cost 8 times what a uniprocessor cost. How could this be? Well, that's because a lot of costs went into memory and disks. And so on the Power Challenge, you were cost effective if you got a speed up greater than 8.6. Okay, and going into these multi-cores, you know, I believe you're going to be cost effective at much lower speedups because the cost up, the marginal cost to your whole system of adding a few cores on a chip is going to be quite low. You'll be cost effective, as we as engineers are not going to be very satisfied, but that is something that's a little bit more rosy looking. All right, so how might all this evolve with servers and clients and in the embedded space? Well, this is going to be largely good news for Google. So in the 1970s, where in the Watergate scandal, there was a secret source named Deep Throat, Mark Felt, who recently died, and he wanted to help people without actually giving himself away. So he'd only confirm information but never provide information. And he used to say frequently, follow the money. Follow the money. Well, going forward, I recommend follow the parallelism. You know, where parallelism helps performance and where parallelism helps cost performance, computing will flow. And servers obviously can use vast parallelism with tremendous engineering challenges, yes. However, on the client and embedded side, it is an open question. But there are people who are going around saying, well, computer science advancement is going to end if we can't make multi-cores work on a desktop. And I think that's totally false. It's guaranteed to work for servers once we engineer it right. And if clients and embedded don't work, well, the center of gravity of the computing universe will move. Okay, so that was symmetric chips and some software things. What about asymmetric multi-core chips, also called heterogeneous? Okay, symmetric required all cores to be equal. What about enhancing some but not all the cores? Okay, so for Amdahl's simple assumption, of course, it makes sense to only enhance one core and leave the others base cores. And what are the techniques for doing that? They're not the subject of this talk. So how does this affect the hardware model? Well, we're still bounded by n resources for the cores. We're going to spend r resources on this one bigger core, and that leaves n minus r for the other cores. They're all base, so there's going to be n minus other base cores. And for a chip of 16, here's our symmetric one. You could have 4 BCE cores. And now for asymmetric, you can have 1 4 BCE core and 12 1 BCE cores. So is this chip over here going to do better or worse than that one? Actually, it's not depends. It will always do better, under the small assumption that it's not hard to develop the software for an asymmetric chip. Okay, so how do we analyze this with this model? The serial fraction is the same. It's the serial fraction divided by the rate. On the parallel side, you're going to have one core going really fast and n minus cores going at rate 1. We're assuming that load imbalance is not a problem for you brilliant software people. And you get a speed up according to this equation. Okay, we go back to our square root assumption. First of all, before I look at the lines, let me define the axis. It looks very similar, but now instead of applying these RBCEs to each of the cores, you're only applying it to one core. So if you only give it 1, it's still symmetric. But for example, 4 leaves 1 enhanced core with 4 and 252 base cores, and so forth. Okay, so how do asymmetric and symmetric speedups compare? I already gave it away. The asymmetric ones are always better. So here's our symmetric one again. And so for example, at 90% parallel, we got a speedup of 26.7. And for the asymmetric, we more than double that speedup to 65. Yes?
But aren't you assuming that you actually can enhance that megacore?
I'm assuming that, yes, we architects can enhance that megacore and that you software people can use that megacore. And part of the reason I'm assuming that we architects can do that is I'm trying to make the case to people like the National Science Foundation that they should still fund things who are trying to enhance cores. There's a current belief that, well, all we should do is deploy little dinky cores and that will solve the problem. Yep.
In these graphs, are you assuming that the microcores are just one unit?
The microcores are just one unit.
Use 1 unit of BCE as opposed to varying the number of units for the small.
The small cores are all base cores. For Amdahl's simple software assumption, it makes sense to spend all the enhancement on one core and leave all the others base. Now, I doubt that's really what you want to do for real workloads. Yes?
Let me ask the question maybe more clearly. In the previous model, the performance gain from doubling, quadrupling a core was square root.
Right.
I didn't see a square root.
Oh, right. So this is the same as before in the sense that the equations use any analytic or empirical function performance, and the graphs are going to use square root. So we're going to assume that all these enhancements are done and you're only getting the square root back. Now, it's still an open question whether you can even get the square root back for, say, a core that's using 128 resources. But, okay. All right, so how do the speedups compare? So this was 26.7, and with the asymmetric, you more than double that. It also works when you're much more parallel. So if you're 99% parallel, your speedup, if you could do all of this, goes from 80 to 166, doubling. Okay, so asymmetric offers greater speedup potential than symmetric. And in the paper, you can see that as Moore's law increases n, the resources for the whole chip, the benefit of asymmetry expands, okay? And so the flip side of this is that when you go back to more modest chips, four-way chips, the benefit to asymmetry contracts. And that's one of the reasons why we haven't seen too many asymmetric chips, because the potential benefit is small. You know, the practical issues of dealing with are not worth confronting. But I think that could easily change. Now, one example of an asymmetric chip, when I gave this talk, IBM pointed out that Cell is an asymmetric chip. That may or may not be a positive example. All right, so there's all kinds of software issues for asymmetry. How do you schedule? How do you manage locality? How do you synchronize? And what level do you do this at? The higher level you go up, the more you potentially know. The lower you do it at, the more you leverage. If you can do all this in the hypervisor, all the programs running on top of the hypervisor benefits. And there's lots of issues, and we'll talk a little bit about applying this to a warehouse scale computer. These issues are going to apply at the warehouse scale level also. Okay, dynamic multi-core chips are the third kind of chip. Children and computer scientists like to have their cake and eat it too. So what if you could have all n-based cores, all the resources in the parallel phase, and then you could somehow harness a bunch of the resources together at no opportunity cost in the serial phase. So here's one sort of picture of it. You got all these resources in parallel mode, and then you go to sequential mode, you somehow gang them together, and they act like a big sequential processor, and so forth. Now, this is one way to do it. There's another way to do it, which I think is actually likely. The first way is possible. This one I think is likely. So assume that your limiting resource is power, okay? You can only spend so much power because that's what you can bring in, that's what you can cool. And you're no longer so limited by area, okay? Let's assume we're unconstrained by area. Then you can build the following chip. You can build a chip where we power up the little guys in parallel mode using our full power budget of n. And when we get to sequential mode, we power up a potentially big sequential processor, and we use our whole power budget there, and so forth. And this is pushed by Guri Sohi and some of his students. Now, the interesting thing is that both of these models, or both of these kinds of chips, fit the Amdahl model the same way. That in the parallel mode, there's no opportunity cost. You get to spend all base cores on the parallel mode. And then in the serial fraction, you get as many as you can put together up to R at performance R, which in the equations is an arbitrary function, in the graphs is the square root. Okay, so what does this look like? The equation looks like this. What do the graphs look like? Well, here's our asymmetric graph, once again, and here was our 99% parallel, and we had a maximum speed up here of 166, and you'll notice if you spent more resources than that, than the 41, it was non-optimal. Okay? In this dynamic thing, it's not going to happen. There's no downside to spending more resources if you can. So what we'll see instead is that the curves always keep going up. Okay? And so potentially at 99% parallel, you could increase your speed up to 223. There's a slight problem. We just don't know how to do this. But the model says that it's possible. So dynamically adjusting the resources has greater potential than asymmetric. So I argue that should be studied as well. It has all the issues of asymmetric, only worse. And I actually believe that dynamic chips, because of the limit of power and area becoming less precious, are likely. Not everyone agrees with that, though. All right, so let's do some caveats and wrap up. And first, I'll begin with some comments on warehouse-scale computers. So I recently read a draft of Barroso and Holzel's warehouse-scale computers, which is this synthesis lecture in computer architecture. I edit the series, and these guys are trying to explain to the world a little bit of how you guys do business. And so in reading this, I was trying to think about how what's happening there how it interacts with this Amdahl model. Well, first of all, within a warehouse-scale computer, you have nodes. The nodes are going to be multi-core whether you want it or not. And so there could be some issues within that chip. You know, do you want for your workloads static and dynamic? What would be the asymmetry? What would be the implications of that if some cores were faster than others on a chip? We probably got to extend the model because you're going to have to be very concerned with thrashing the last level cache and the memory bandwidth. If everything on a given multi-core chip is doing independent stuff, you're not going to get anywhere near the core's potential. But a more interesting question is what happens if you pop up and say, let's think of what was our node, or what was a core in our model so far. Let's make that a node. So let's pretend that we're going to do this for a warehouse-scale computer, and we have these nodes. And Google spreads its work among the nodes. A query fans out, does some parallel work, and fan in. So what are the implications to looking at this computer system with the model? Well, you still have to adapt to some performance function. If the nodes of your warehouse-scale computer, you want to buy a faster node, you know, it's probably not going to get performance that scales linearly with the cost. You're going to pay some premium. Maybe it's the square root. So do you want to do this? Do you want your nodes to be symmetric, or do you want some nodes to be faster, either statically or dynamically? What's the best way to achieve this asymmetry? What about Amdahl's model? You know, we were dismissing it before, but does it apply? You know, the bad news here, if it's 99% parallel, your speed up is limited. So an interesting question is, what are the fraction parallel for Google's workloads? I guess you would call this the G. Well, fortunately, there's some interesting work on this subject. Instead of looking at the fraction parallel, it looks like the fraction serial. So kind of like sometimes it's useful to look at miss ratio as 1 minus the hiss ratio. So let's zero in on the fraction serial. There's this great paper by Karp and Flatt, which is also a Wikipedia article, which says that you can, with some quick math from Amdahl's equation, it's just simple algebra, you can compute you can estimate the fraction serial by looking at the time on p nodes divided by the time on one node, and then subtracting 1 minus p, and you can read the denominator. And this is nothing magic, it's just algebra. And the interesting thing to do then is to say, we can now empirically measure this fraction serial for varying p. Now you say to yourself, Mark, what are you drinking here? The fraction parallel is not supposed to change. Well, yeah, that's in Amdahl's model, right? But for real software, it could change. And one of the things you can look at is what is the fraction parallel at a given p, and what happens as you increase the number of nodes in your warehouse scale computer. Is it stable? In which case Amdahl's model is doing a good job. Does it increase? Does it decrease? If it decreases, actually, that's kind of a bizarre result. It usually means some superlinear caching effects. But I think there's a lot of interesting questions there for understanding your workloads. What is Google's fraction parallel? All right, so here are our three equations, putting them all on one place. And we see that the sequential sides are all the same, and then the parallel sections differ by enhancing all the cores, enhancing one core, or basically paying no opportunity cost for enhancing cores. All right. I'm an unusual academic. Instead of, I will actually admit that this work is not perfect. So you could make some charges about the software model, that the serial and parallel fractions are not totally serial, not totally parallel. Yes, this could be extended to tree algorithms and bounded parallelism. You can say that this notion that you do the same thing when you have a larger machine is absurd. When you have a bigger machine, you actually solve a bigger problem, maybe in the same amount of time. That's true for weather prediction, right? You need the prediction for the 6 o'clock news. Bigger machine, you get a better prediction. This is called weak scaling by Gustafsson. I think prudent architectures have to support strong scaling, and there's also an argument that, at least within the multi-core chip, weak scaling is hard because you can't just scale the memory capacity and memory bandwidth arbitrarily large. What about synchronization, communication, and scheduling? You can extend for this. Software challenges for asymmetric and dynamic are worse, absolutely true. And then finally, my favorite argument is future software will be totally parallel. See my work. And I'm skeptical. Even your MapReduce is not completely parallel, right? You have to fan things out. You have to do some work. You have to fan it back. All right, so this is easy criticisms for me to make because these are really criticisms of Gene Amdahl, who's now retired. What about our hardware model? So it's naive to bound the cores by one resource, especially area. Well, we're not really doing area. It can be any kind of mix of things. It's naive to ignore the off-chip bandwidth and the effects of last-level caching. Absolutely true. Okay, why did we ignore it then? It's because we didn't know how to characterize workloads. It required too many coefficients to do it. Not that it wasn't important. It's naive to say that the performance grows as the square root of the resources. Well, that's only the graphs. The equations can use any function, including an empirical function. And finally, Mark, you're running things into realms where we have no idea how to do this. Well, that's exactly the point, right? This shows the need for this if we want to effectively use multicore, so we should figure out how to do it. So you can go to our website and you can actually play with some Java where you can put in your own functions and see what the graphs look like. But more importantly, computer scientists and architects should work together to try to make this third Moore's law happen and double the parallelism. And ultimately, we don't talk about digital computers anymore. Digital is implicit. And the same thing has to be true with parallel. We're only going to be successful if in a couple decades we talk about programming and computers, and that is parallel programming and parallel computers. So I'd love to see where we go up to 1,000 base core equivalents and we get a speed up near 1,000. And we certainly can't do this today, but if we don't do some work, we want to try and succeed or fail. We don't want to fail by not trying. So in this talk, I've developed a corollary to Amdahl's law, which is a simple hardware model that just goes from some very basic assumptions about fixed resources for cores and sublinear gain with resources. And from this, several interesting conclusions follow. And the second one is was something that people were really going away from. They thought we don't need more core performance, and I think we do need more core performance. We just have to figure out how to do it with really efficient power. A lot of our high-end cores use a lot of content addressable memory, and they're not efficient in power. And I'm optimistic that ideas are out there. And I think we really have to seriously consider these asymmetric designs, not with just one bigger processor, but with many, depending on the workloads. And there'll be many problems, but the potential gap is so large that I think they're worth confronting. Thank you. Yes?
So it seems like perc of R equals square root of R, although it's not a fundamental requirement for your model, is fundamental in the graphic results that you displayed. In particular, did you ever look at some alternatives? The reason I ask is that at best captures the timing delays cross chip area, and that's very optimistic. I didn't know if the empirical measures that you had were actually measures of serial-only code as a function of R area allocation, which is in fact what you're trying to run. If you were running parallel code in a heavily pipelined machine, I'd say, yeah, the microarchitecture challenges there are easy. But if you're running the serial-only section of the code in a very large, heavily pipelined machine, your net efficiency is going to be quite poor. It's hard to get square root of R out of that.
Okay, so there were a couple of questions there, and let me just rephrase them. One is, the simple one is, did you look at other functions besides the square root of R? And we definitely looked at other functions such as changing the value of the radix of the.
Well, so fourth root of R.
Yeah, we looked at some of that, and for modest changes, it doesn't change the results too much. A lot of people, but
Even in your dynamic power, 1,000 core.
I didn't look at it at 1,000. I don't want to say this. We looked at some variations of it. It didn't seem to qualitatively change things too much. But by the way, I don't think you should take these qualitative results at all seriously, right? I mean, this is just to illustrate some larger trends. Now, to your other point, which let me rephrase that as, wait a second, Mark, the only thing you're trying to run on this bigger processor was something that's pretty serial. How are you ever going to get speed up on it? That's a legitimate question, and I don't know the answer, and maybe we can't.
I'm not saying it's not a good question or not a good thing to try for. It's just I thought we've been using a pickaxe on some of those issues in terms of branch caches and pipelining and speculative execution and wide instruction words and
Right.
we've kind of been after that.
I have no idea how to do this. The idea was to show the need that it should be done. And if there is there's a need for it to be done, then people will try pretty hard, and they may fail because it can't be done. But we hate to have them fail because we didn't try. Yeah.
I was going to say in your defense, you can imagine that whatever the biggest processor is the biggest one we know how to build today, and the smaller ones are smaller than the best we know how to build today, and there's still some power benefit to that type of arrangement.
Right. And so the statement was, some of these processors, we know how to build some big processors, we know how to build some small processors, but that's only today's designs. There are more possibilities. In particular, on the big processors, kind of what happened was we were building processors caring about performance only, and then power was considered sort of at the end. And then suddenly we've had this pullback to more modest cores. And I'm arguing that we should revisit building those higher performance processors when power is a first order initial consideration, and there may be solutions out there. Yeah.
So there is some evidence that the cost function might be the logarithm instead of a square root, in which case the conclusions might.
So if the cost function is the logarithm, rather than the square root, then yeah, the diminishing returns will get serious pretty seriously. So you can go to our website and just plug in logarithm and see what the graphs look like.
An architectural question. The processors have swallowed up various other chips in the system, floating point units and whatnot, but except for one, which is main memory. Will gaining a high sequential performance require the integration of main memory onto the processor chip?
Okay, so the observation was that the processor chips have swallowed up many kinds of chips except principally not main memory. I'm skeptical that main memory will be absorbed except in those instances where you want to live with relatively small main memory. Our ideas always seem to want more main memory, and the values, when you want a lot of capacity of specializing the semiconductor processes to logic on one hand and DRAM on the other hand, seem pretty substantial. But I can totally believe that we could get, you know, mobile phones of the future that have one chip. The other thing is there's many engineering games to be played to improve the bandwidth between a few memory chips and the processor chip. Improving the latency is very difficult, but improving the bandwidth, there are many difficult engineering techniques, but sort of normal difficult engineering.
A lot of architectural research has treated different types of parallelism differently, in particular thread level parallelism and instruction level parallelism. Are you collapsing those down to a single axis for this analysis, or do you think it's worth doing that?
So the question is that a lot of architectural research has treated like instruction level parallelism as very different from thread level parallelism. Well, I was basically using Amdahl's law, which says that there's thread level parallelism on the one hand, and I guess the fact that you can actually enhance the performance of a core is assuming that you're doing something, which has to be partially exploiting low-level instruction level parallelism. Whether we want to combine the two in the future, that's well beyond the scope of this simple model to answer. Yep.
So Google, we built these warehouse computers out of nodes and multicores. So rather than these larger enhanced cores, what about the trade-off of how big the node should be versus the hierarchy versus
Right. So the question is, instead of talking about the cores on a multi-core chip, why not think about Google's issue where, in some sense, what is a core in this talk corresponds to a computer as a node in a warehouse scale computer. Well, I have thought about it a little bit on the airplane out, and I think a lot of the arguments that are made in this talk will also apply to Google's situation, that you will want to have some enhanced nodes. Now, enhanced nodes will not mean that Google enhances them necessarily. It means that Google will pay, a price premium to have some higher performing nodes to get the sequential performance when you're near the bottleneck of your work. Or did I not answer your question?
Yeah, my question is confused. So we have this question about how big should the node be? Should we put more cores on the node or have more nodes? Does that make sense? That similar to your enhanced node.
Right. So you're saying, okay. So one of the questions that Google wants to answer is, should you put more cores on a node or have more nodes? Yeah, that's a question that has to be answered. It's a hierarchical question beyond the scope of this simple model. And, the trade-offs are going to involve what the cost-effective curves look like. But I think as you get large enough, there's going to be pressure to go for this asymmetry. And there'll be pushback from software because obviously there are tremendous challenges. I don't have any magical answers at this time. Yep.
So in all these graphs, we have assumed that the fraction parallel is staying constant with the increasing number of cores. Well, I think that in some cases the fraction parallel probably goes down. We'll have more logarithm.
Right. So So the question was, these results use Amdahl's law where the fraction parallel is fixed. And you say that it's likely that the fraction parallel will go down. One way that'll happen is John Gustafson's result, where he says basically when people get bigger machines, they compute for the same amount of time on a bigger problem, and the parallel side grows faster than the sequential side. You know, if that's true, we're in salad days. And I think it depends on the problem. For architects, I got to believe it's not true for all problems, and so we have to architect chips for the more pessimistic Amdahl assumptions. For Google, that's a good question for you to ask as you get to more applications and more, as your workloads grow, what does happen to the fraction parallel? I mean, if you got to fan in on a tree and fan out, it's not going away.
One last question. Analogous to your cost up, one thing that might be an interesting small addition of complexity to your model would be to consider something more of a power up equivalent. That is a system level effect, right? You may have a core potentially that is very power hungry, but because of all the other electricity consumed in things that are non-core related, that inefficient core may make for a more efficient overall system. Have you looked at that at all?
I haven't looked at that specifically. Of course, that cost up argument, you can treat cost in any dimension. It doesn't have to be dollars. It could be power. But the basic thinking that what you said, I guess I didn't repeat what you said. Luis's question was, if you looked at the cost up stuff, have you applied it to power? I think the basic sentiment definitely holds, right? Is that if you have all this stuff sitting around burning power, it might be worth being locally inefficient in the core to make sure you're utilizing all this other stuff which is burning a lot of static power. And to the extent which you can scale back that static power, which you're arguing for, then there's less pressure. But it's definitely something I think that should be a first order consideration, not something you think about after the system is deployed.
Maybe we'll wrap up. He was happy to come here afterwards and talk to
Okay.
Mark. Thank Mark again.
Thank you very much.